So let's start this eMeetup. Very welcome, Daniel, to this data science eMeetup. Nice to have you here. Today's title is Keyword Search is Dead, and so are Solr and Elasticsearch. I'm very looking forward to your talk. A few words to your background. So you did your studies at LMU in computer linguistics and are now working at SHI GmbH as a lead consultant for search and analytics. So you, from your CV, have a lot of experience in that topic. And I don't like to tell too much about the topic. Hand over right there. Very looking forward to what you have to present today. Again, for the cloud, please feel free to ask questions anytime. If you have questions, you can also put them in the chat. Sarina and I will have a look at the chat and then read them out loudly. Daniel, the stage is yours. Please go ahead.
All right. Yeah, so thank you for this introduction and a warm welcome from my side. I've been in the world of search for almost 9.5 years now, so I am really excited to tell you something about the latest evolvements around search. And before we dive into the details there, let's just, have a brief look at the title that I gave it. So I chose a rather provocative title stating keyword search is dead. So we kind of need to first dive into, but very briefly, the topic of keyword search so that we know all about, what we are talking about and what is it that I am claiming to be dead. So I don't need to introduce myself because that's already done. We'll start right with what's the problem with keyword search, or rather, what is keyword search in the first place? So every one of you uses keyword search rather frequently, be that shopping on Amazon, Googling stuff, searching for the next tram that goes from, wherever you need to go to. So everyone knows basically what keyword search is because you all use it, but you may not be familiar with, let's say, what happens inside a traditional search engine. And that's what I'm going to start with today. So I have, let's say, a smallish diagram here, kind of outlining what a traditional search engine is capable of. And we'll start with the bottom left corner here, where it says documents. Documents can be basically any type of data that you want to, search in. So that can be an article, a product, that can be a log line, that can be an event. So basically everything that you, want your users to find, that can be a document. And when you want to index that, so indexing is basically storing something in a search engine, you kind of need to pre-process the data. And pre-processing in terms of the most popular search engines, Solr and Elasticsearch, means going through a so-called analysis chain or being, applied to a mapping. And what happens in this analysis chain is you kind of break up and, pre-process the data that you want to index. Now, what does that mean? So if you have a document, and I've outlined here a couple of exemplary steps, it first comes to a so-called tokenization step. Tokenization means nothing else than your input is just segmented into single words or tokens. So if we have an input like we see it on the top left corner, let's just say the quick brown fox is our input, then the tokens would be the quick, brown, and fox. So we would have 4 tokens left after the tokenization step. Next step would be lowercasing. That's kind of self-explanatory. So we kind of lowercase all of our capital letters to small letters. Next step here outlined is character normalization. So in Germany, we have umlauts, ä, ö, and ü. So we kind of need to work these out so that someone who hasn't got these characters on his keyboard maybe is also able to find stuff containing umlauts. Or it can also be getting rid of HTML markup, for example, or weird hyphenation characters or punctuation characters. So anything on a character level that can be character normalization. Next step outlined here is stop word filtering. So we have in each language words that don't have a lot or even any meaning. That can be the, and, or, this, that. So everything that you don't really want in your index or that users don't really use to search for stuff in your index, you can throw that out with stop word filtering. Then we have a step called stemming. So that is used to, for example, search for the plural form, but also find singular forms. So you search for dogs, but you also find articles or documents containing dog, so not the plural form, right? So you have only the singular forms indexed, so you have better recall in terms of information retrieval. Last step in this example is synonym expansion. So if you don't want your users to know all the synonyms, you kind of do the work for them, apply synonym lists, and then you can say jumping is the same as leaping or house is the same as building. So you can kind of enrich your data when you index it. What we have in our index is then a list of terms, and we have them mapped to the document IDs where these terms occur in. So in our index, for example, we have the term dog, and we have the IDs 1 to 3 applied to the term dog, which means that the term dog occurs in documents 1 to 3. That's basically how an inverted index, that's the concept called, is built up. So if we now search for data and our query on the top left corner is called the quick brown fox is leaping over all the lazy dogs with 2 exclamation marks. We also need these pre-processing steps so we can match the terms that we query for with the terms that we have indexed. So first step is tokenization. After tokenization, we have the, we have quick, we have brown, we have fox, and so on as single tokens. Next step is lowercasing, so the capital T, the capital D, O, G, S from dogs, these are all lowercased. Next step is character normalization, so maybe the inverted commas are thrown away or the exclamation marks are thrown away, so everything on a character basis. Next step is stop word filtering, so the, is, over, all, and the. These are all non-really meaningful words, they are thrown out. Next is the stemming step, the plural form of dogs, and the ing form of leaping is getting rid of. And then we have the synonym expansion, where we substitute, in that case, not really expand, the term leap with jump. And so we search for quick, brown, fox, jump, lazy, and dog. And well, let's see what we get when we query the data. And search technology is perfectly and really efficiently able to then retrieve all the documents containing these terms, either all the terms or only one of them, depending on the configuration that you chose for your search scenario. So now we know how well this inverted index concept works, how traditional keyword search works. And next step is we kind of need to know how do you kind of judge which document is better than another one, because usually you don't have only one hit, but you have maybe 10 hits or 100 hits. Or if you go do a Google search, you may have 1 million hits, and you kind of need to know what is the best hit. In traditional keyword search, we have something called BM25 scoring metric. And this is now used to identify the best, the second best, and so on, hit from your hit list. BM25 is really old. It's been developed in the 1960s, 1970s. And this is still the default in traditional keyword search engines like Solr or Elasticsearch. Why is that the case? So it really works well for many use cases. So this is nothing about old stuff not being good. Old stuff still is good in certain cases. So this is kind of where usually the work starts for search consultants like me. You kind of have a couple of factors. BM25 rather nicely balances. That means that BM25, you have this formula down there, but it all comes down to the documents that have more frequent the terms that you searched for, they are more relevant. Yeah? If you have rare search terms, then these have a higher weight than you have rather frequent search terms. So if you search for the dog, you don't want the document containing 1,000 thus. Hit number one, you want the one containing dog number one, right? So if you have very frequent words, you don't want them to kind of spoil your frequency measure. And then you have something called term saturation. That means nothing else than if you have a hit in a small document or a rather short document, this is more relevant than something in a very long document. So just think about you have a hit in a, well, let's say email style of text, which is more or less maybe only a paragraph long, or you have one hit in a 1,000-page book. Which one is more relevant? Probably the email, because the whole email will deal with this one keyword compared to the whole book with 1,000 pages. So these are basically the factors that are used to make up this BM25 scoring metric. We don't need to dive into the details here. Just keep in mind term frequency, document frequency, term saturation. These are basically the three factors defining relevance. So if we now think about that, and also how we build up our index and how we search in our index, we see that we are not really capable of handling ambiguity. So in Germany, for example, we have a word called Bank, which can be a bench to sit on, or can be the financial institute where we want to withdraw money from. And if we only search for this keyword, well, our keyword search engine doesn't really know, do we mean one or the other? Also, not really the searcher's intent is identified anyhow. So the search engine doesn't really know anything about me because it only has, well, keywords indexed without any context of the word, without any context of the persons or users searching for. It's also not really handling kind of approximate matches. So if I search for vacation in Northern Africa, I don't care whether that's vacation in Tunisia, in Egypt, or Morocco. But the keyword search engine, it may only know, well, Northern Africa, for example. So we kind of need to either manually implement all this intelligent stuff in our keyword search engine, or we need something which is a little, well, more intelligently handling things. And this is where embeddings come into place and also vectors come into place. So now we know how a keyword search engine works. We know of the difficulties a keyword search engine may have. And now let's have a look how we may be able to overcome these obstacles if we tend to embeddings and vectors. So what are embeddings? This is a data science meetup, so probably all of us kind of at least know what embeddings are and vectors are. So we'll do a quick intro on that one as well. So embeddings are basically vector representations of non-numerical objects, in our cases at least. So we can kind of convert images or text or audio, any unstructured data, to embeddings or vectors. You can imagine it if we have a text search engine. If we train an artificial neural network and we want to predict the next words for a given word, then we have a byproduct. And this byproduct, when we train this artificial neural network, that's the weights of the trained network. And what we can do with these weights is we can use these weights and reformat them so they represent a vector. A vector, of course, is again something based on numbers, so an array of numbers or an array of arrays containing numbers. And now that we don't only have a term or a word or a token that we store, but now that we have vectors, we kind of have context around it. We don't only have a couple of characters, we have context for these characters, basically. So with these weights, we have meaningful predictions for the network. And this means that these weights that we have, they are also meaningful. And now what we can do, because vectors are basically based on numbers. We can compare vectors to each other and we can say, okay, how different is one vector to another vector? And the distances of two vectors, they tell us something, well, how similar these vectors are and how these words may be related. There are a lot of distance measures that you can use for. So for example, the Euclidean distance, the inner product, the Jacquard distance, the Tanimoto distance, the Hamming distance. So there's a couple to think about when you dive into these vector search engines, because not every distance measure works for every use case very well. So this is something that you usually, well, have a lot of testing done on if you go into the vector distance space. But the important thing here is that there are distance measures, a couple where you can choose from. When we try to, well, draw a picture, and having vectors of a lot of dimensions is not really something you can draw very nicely. But if we have everything in a two-dimensional vector space, it's a little easier. So in that case, we have, well, vectors as dots in a two-dimensional space. And now we can say, when we're looking at text search again, that synonyms, so words with very, well, similar meaning or even the same meaning, they will be located very close to each other. And also words that are, well, similar to each other, may not the same thing, but belong to maybe a certain concept. They kind of are co-located, at least in this vector space. And what we see here is, for example, right at the top, we have a lot of green dots, which represent body parts. The top left corner, we have a lot of red dots, which are cities. At the bottom, we see relatives, so something like family, husband, wife, children, and so on. They would be located there. So what we have in this vector space is basically, well, implicitly encoded information that we usually need to, well, think about for ourselves if we do everything the hard way. So when we now query a vector space, we can take the query, we encode the query as a vector. We try to find, well, the most similar results to our query vector. So we have kind of this, well, similarity search engine now that we need to think of. We don't really have something like a very exact match usually, but something similar. And what we have in case of text is we have relationships, semantic relationships, implicitly encoded in our vector space. So as we don't only store terms, keyword terms, but, well, the context also of these terms, we have implicitly something like synonym lists, like taxonomies, like ontologies, also indexed in our vector space without really telling the search engine that building is very similar to house and my grandfather is a family member and stuff like that. So we have everything implicitly encoded without really worrying about it.
Can you, maybe I have one question if you can do that. So maybe you can explain what happens in such an embedding with like opposites, like good and bad, for example, because I would assume they are not that far away in the embedding, aren't they?
Not that far away in the embedding. That's a good question. So I think it would depend probably on the model you use to really encode these words. So good and bad are very good, in that case, examples, because if you search for something like, let me just think of an example where we can see how this relates to keyword search. So if you search for, oh yeah, that's a good one. So clothing, right? If you search for yellow t-shirt, and then you have like someone stating about this yellow t-shirt that it works or fits perfectly well to something else. And the next comment is maybe it does not really work well, or that it really fits badly maybe towards something else. And then you have this concept of, well, both contain yellow t-shirt, but one does not work well with a yellow t-shirt, the other one does work well with a yellow t-shirt. So they could be really semantically encoded in a similar way because they have the same context. So in that case, I would agree. In another case, I would say, if you encode also not only the surroundings, let's say in full text, but also from user interactions. So how is this word being used for in queries? That way you could kind of, let's say, fine-tune a general language model and put something on top where you also encode, let's say, what was searched for in the past and what was clicked on afterwards, to bring in not only language information, but also user interaction information, and kind of go that direction and take a purely language model a step further. That's maybe better.
Okay, understood. Maybe I will come back to it later, but first I'll let you continue because maybe some of the follow-up questions will be answered.
Okay, all right.
Thanks.
So in general, I would say it's easier to encode, let's say, nouns than it is to encode adjectives, for example.
Makes sense.
And it definitely depends on your use case, how well encoding adjectives really hurts you. So that's rather specific, but I think, yeah, the concept of nouns is almost always the most important one when it comes to search applications. But good question nevertheless. All right, so turning back to the slides, how does now well, overview of such a, let's call it, vector search engine look like? And we'll also see here one of the components that we've just talked about. So we also need, when we are using a vector search engine, we kind of need to index our data and we need to query our data. So that doesn't come as a surprise. And if we want to encode documents as vectors, we also need, let's call it, some kind of basic pre-processing steps, but they make up, let's say, not the main part of the pre-processing here, but we still need to tokenize our input. We still need to lowercase our input. We still need to normalize our input. And then we can use, well, in terms of a search engine searching for text, we can use pre-trained language models like the one that Google, well, I wanted to say outsourced, but it didn't outsource it. They published the BERT model, and it was yesterday, 3 years ago. So the BERT architecture is now 3 years and 1 day old. So we have perfect timing for this slide here. The BERT pre-trained language models, which are out there, they can be used, let's say, for your general language understanding. And then what we generally need to do is we kind of need use case specific training data, because when these hugely pre-trained language models, when they are trained, they kind of try to represent more or less the general German language, for example. But the general German language is not what your users use, for example, when you're having, when you're an online shop guy trying to make online shop search, sorry, as relevant as possible. So you kind of need training data on top on generally pre-trained language models so that you can fine-tune these and well, have really your use cases reflected well in your vector space afterwards. So what do? We take the documents, we pre-process them, we use pre-trained and fine-tuned language models to convert or encode our content into our vector space. And this is what we then, well, have stored in our vector search engine. And on the query side, we kind of need to do the same. So the same means we have a query, we do pre-processing on the query, and we use the same models, the same fine-tuned models, to encode the query into a vector of the same length or the same dimensionality in that case, so that we can compare the query vector with all our document vectors that we have indexed in our vector search engine.
Sorry?
Yes.
So to understand correctly, you say the whole document is embedded as one vector. So not
Correct.
the words, but the whole document.
Yes, that's it.
Okay, how do you do that?
Well, how do we do that? Yeah, we take the document, we do pre-processing on this document, and then we have the language models that encode our content into a vector of, let's say, 512 dimensions or 768 dimensions, and that's what we store in vector search engines.
Okay, but I thought like something like BERT would encode every word into a vector. Is that wrong?
Okay, so there are different models, and what we have here is the BERT pre-trained model. That is correct. So what we can do is we can use the encodings of each word and make up a vector with these, let's say, sub-encodings for these small vectors. So we have something like a document vector, and then we can do the same stuff for the query as well. So if we only have one word as a query, of course, we can't really put more than one word in that vector then. But if we have more than one term or more information that we can encode, we usually come to, well, the same dimensionality that we need to compare these vectors to each other. So in that case, we have depicted the pre-trained language model based on BERT. There's also other stuff, for example, doc2vec, which is probably the most obvious one, where you can vectorize one document and then you have one vector per document in that case. But how you really, let's say, structure your vectors or what you want to encode in your vectors and what models you want to use, that's basically up to you and your use case.
Okay.
Maybe I just take down a note, and maybe I can show you, if we have enough time, a couple of lines of code to, I think I should be able to depict that maybe in a couple of lines. So
that would be cool.
Let's see. We should have a couple of minutes left afterwards. So excellent question. We'll turn to that smallish detail later on. The key is here, document vectors, query vectors, they need to be of the same length. If they are not of the same length, you can't really compare them. That's like, well, Äpfel und Birnen in Germany, yeah? Apples and pears that you can't really compare well to each other. Right, so if we now turn towards what current solutions do we have in the search landscape to see, well, how the search landscape really is made up of these technologies. Of course, we have what kind of is very widely used nowadays still. The, well, inverted index technologies like Solr and Elasticsearch, or OpenSearch, which is kind of the, well, open source Elasticsearch variant, since they kind of did their license change earlier this year. They are all based on Apache Lucene, and they all use BM25 as the default similarity engine in that case. There are also pure vector search technologies like Weaviate or Milvus. There are also other ones, but these two gained, let's say, a lot of attention within the last couple of months or even years. So they are kind of purely there to, well, provide infrastructure, provide also the technologies so that you can store vectors and search in these stored vectors. And then there are also hybrid search technologies like Haystack or Vespa, where you can combine BM25 and also vector search approaches with each other to more or less bring the best out of each words together. We also have proprietary software. So for example, LucidWorks Fusion, as a disclaimer here. So we at SHI, we are LucidWorks Fusion resellers. So that's kind of why we mention it, of course. What they combine is they combine Apache Solr and Milvus in their product Fusion to also bring together BM25 and Vector Search. There's also Pinecone and many others who have a managed vector search offering. So that's kind of, well, vector search as a service in that case. Weaviate and Milvus, the companies behind these. So one is called Semi Technologies, the other is called Zilis. They also have, let's say, proprietary offerings. So if you don't want to manage that stuff yourself, you can turn to these companies and they can also, well, run it for you, and you are all only using it as a, well, software as a service offering in that case. If you only have a smallish use case, you can also turn to libraries for similarity search. The most popular ones, I guess, at least at the moment, are NMSlib or Face, the latter one being developed by Facebook. So that's kind of, yeah, the popular kids on the block right now. So if you don't want to, well, or if you don't need to think about scalability, operating stuff, and so on, if you only have a smallish use case, turn to a library. If you have a larger use case, turn to the vector search technologies. If you don't want to manage it yourself, go to the Pinecone guys or the offerings that are behind the open source engines. That's kind of where you turn to if you need a vector search engine in that case. So now that we know a couple of the solutions that are out there, are vector search engines the perfect solution? And we're going to dive into real quick a couple of use cases where you can use vector search for. So in the recruiting business, you can, well, store vectors of candidate profiles, and then you can use your job postings, convert them to vectors, and then, well, search with the vectorized job postings in your candidate profiles to retrieve the best matches in that case. So recruiting, you always have a lot of, let's say, highly specialized terminologies. So we are all, let's say, in the IT business. So we know that a software developer is very similar to a software engineer. We know that a Java developer is a software developer. We know that, for example, Apache Hadoop is something within the IT and software development world. But that's something that changes really fast, and you really need to be up to speed to feed that information in manually. So if you kind of outsource that into your vector search engine, that's a good thing to do. You don't need too much expertise then to search for that data. You have higher recall and a higher accuracy when matching your job postings to the indexed candidate profiles. When you're working in law, you kind of want to really quickly find similar cases than the ones that you're currently working on. So you have indexed all court decisions from the past. You use your own cases that you're working on and vectorize the data, search in the index data, and then you find, well, the precedents that you can quote when you're at court. When turning to the chemical industry, we have molecules, and molecules is something that is completely unrelated to text. So that is unstructured data, but not text unstructured data, but completely different. So this is something you can't really do well with Solr or Elasticsearch, at least not purely. So you would need to implement, let's say, well, third-party plugins or anything like that. But when turning to vector search, you can vectorize your chemical fingerprints as vectors. You can store these as vectors, and then you can find similar substructures and also superstructures through this molecular search, which helps you to discover drugs faster and also get them faster into production. Next case is from biology, where you have DNA sequence matching. So DNA is also something which isn't really text. So again, unstructured data, but in another way than text is unstructured. And you can vectorize DNA sequences and store that rather efficiently in a vector search engine. And that helps you classify sequences with a higher accuracy, leading to cost reduction in production or in research. Last but not least, e-commerce. And I read that, I think Otto, I read that this morning, but I haven't dived into the details. So Otto uses vector search for handling 0 results, just as depicted here. So what you do in the background is you store all shop interactions somewhere, you vectorize that data, and then you kind of try to identify the query intent by finding similar vectors that you have indexed based on the shop interactions from the past. And handling 0 result hit lists is kind of one of the major goals of any online shop, because when your users don't find anything, they won't buy anything. So that's kind of what you definitely need to do. And there are services also out there that claim to prevent up to 90% of your 0 results. And that brings you basically, well, up to 5, 6, or 7-digit numbers, added numbers in revenue every day. So vector search engines are very useful for a couple of use cases, but they also have some downsides. And one of these downsides is that, well, you kind of need these machine learning AI models in the background. And of course, there are a couple of freely available ones, but you need to, well, you need to find the right ones. You may need to retrain or fine-tune these, and that's not an easy task. At least it's not as easy as diving into a keyword search engine and kind of fix your content there. Also, ranking is harder to understand and also to manipulate. If you want to know why a certain vector is similar to another one, and you need to dive into 768 dimensions for 2 vectors, that's not like searching for keywords, right? So ranking is really hard to understand if you are working with vector search engines, and you are not really able to, well, let's say I tried the Euclidean distance, now I want to switch to another one. That more or less means you need to rebuild everything, because once you create this index of vectors, you choose your ranking metric, you choose the distance measure that you want to use. This is nothing that you can pass in as a query parameter, for example. So that also gives you a harder time when you want to tune your search engine. When you have, let's say, 90% of your queries that work really well and 10% don't work really well, what you usually do in an online shop is, well, you kind of curate things manually. You say, okay, for keyword A, I want a landing page. For keyword B, I want a boost applied. For keyword C, I want a synonym. And that's something that you can't really do with vector search engines. So it's really hard to tune some queries when the majority works. That's something that keyword search engines are really, well, better capable of. You also have a lot of usability features in Solr and Elasticsearch, for example, so spell checking, more like this, faceting, filtering, and that is coming slowly but steadily to vector search engines. So all this usability stuff that you really need to kind of navigate through huge hit lists, that is present in not present in vector search engines, but in keyword search engines. It's also worth thinking about what do your users expect to find. So if someone searches for Donald Trump and your language model knows that Donald Trump is a president, so why not return all presidents? Well, maybe your users don't want to see any other president. They want exactly all the documents containing only the phrase that you looked for. So something like phrase search is not something that vector search is really good at or shining at. So vector search is really good for finding similar things, not the exact things that users are looking for. Also, exact matches are computationally expensive. So exact matches meaning the most similar one retrieved out of all the vectors that you have stored, because you need to compare the query vector to all stored vectors. And this is computationally very expensive and usually not what you have in your budget. Vector search engines are still kind of an emerging technology, so it's not battle-proof or battle-tested in all use cases, but at least there are a lot of use cases where it works really well. So this kind of leads us to the question, what is currently going on, especially also maybe with keyword search engines, so that we can say what we really can expect in the future and how we can maybe use keyword search engines and also vector search engines maybe in combination to each other. So vector search related technologies and use cases are gaining a lot of attention. So you see startups collecting money. You see Verizon Media, a very huge company, the company behind Vespa, investing a lot of money in their own products. So the Vespa open source products. So that's kind of obvious. You have new players like Milvus collecting a lot of GitHub stars at the moment, at least. And they are getting broad attention. But this means that the traditional search technologies and the products related, they are still widely used and also widely used by, let's say, the large industries or the large companies within the industries. So here we have a couple of customers that use Elastic or Elasticsearch. Here we can see a couple of Solr users. So Lucidworks is the primary sponsor of the Apache Solr project. So everyone listed here uses Solr either directly, open source, or within the Lucidworks product. So we have a lot of companies really using traditional technologies right now, and they won't really turn to something new just because there is something new. In fact, it is the case that all Lucene-based software, they will try to close the gap towards the vector search engines, because you already have an approximate nearest vector search solution implemented in Lucene 9.0. So once Lucene 9 is being published, which is not the case right now, you'll probably be able to use this approximate nearest vector search very quickly in Solr and Elasticsearch and OpenSearch and basically all other search engines that are based on Apache Lucene. What you have in OpenSearch already is an approximate KNN search. And for Elasticsearch, you can already use a plugin called ElasticNN. So that's what you can already do. And that kind of leads us to the last slide where I'm trying to wrap everything up that we've now discussed. So when does a vector search engine pay off for you and your use case? And here are a couple of questions that you need to ask yourself to decide, well, in what direction you want to go. So if you deal with unstructured data that is not text, like images, like video, like audio, DNA sequences, molecules, then I would probably turn to a vector search engine, because traditional search engines are not really good in handling these. Or you need, well, at least third-party plugins, implement your own plugins, or buy third-party plugins. That can be, well, more expensive than turning towards vector search engines. If you already have a traditional search engine in place, I would either wait until Lucene 9 becomes, well, fully available and all the stuff that is in Lucene 9, or you can try to use plugins if you're using OpenSearch or Elasticsearch. That's kind of, yeah, where you can at least do some experiments, whether that brings you a step closer to what you try to achieve. Also try to find out what your users expect. So if your users are really trying to find very, very exact matches, vector search engines might not be the thing you expect. We have a lot of customers from law, from the jurisdictional sector, and they tend to know exactly what they want. They don't want similar results. They don't want approximate results. They want exact matches. So vector search engines don't really bring us anywhere in these use cases. And one thing to think about is, well, hybrid approaches. So if you have an online shop, maybe you want to use a vector search engine to handle 0 results, or to do query intent detection or other query rewriting stuff. where you can really say, okay, I'm using vector search and similarity search approaches to only power one feature and not really the whole use case. And also try to find out what in-house knowledge you have. So if you don't really have a data science team, machine learning experts, and so on, it can be a very, well, a hard or a very timely effort to use vector search engines because they are really hard to understand if you're coming from the, well, non-vector traditional keyword search world. At least that's what we made as an experience when working with our clients and customers. But in fact, yeah, so this is very, very new, very exciting. And also this is, well, helping us solve use cases that weren't really good solvable or well solvable a couple of, well, months or years ago. So this is definitely an area to watch out and keep an eye out. And with that, I am concluding now. So please feel free to give me any additional question or feedback, shoot me an email, connect, LinkedIn, Xing, Twitter, wherever that is. And I'm happy to answer questions now. If there are no, or in parallel, I will try to get back to Maxime's question so that this one is not forgotten or even ignored.
Thank you very much.
Okay, but before diving into those questions, Daniel, thank you very much for this presentation.
A pleasure.
Very informative. So yeah, if there are questions from the crowd, please go ahead to ask them now. Otherwise, I would also suggest to dive deeper into the topic Maxime mentioned. All right.
Yeah, I would have one question. Maybe I missed that, so this Frank. So thanks a lot first for the great presentation. But this approximate vector search that you mentioned, I didn't fully get it, how this works in an index-based environment, or maybe this was a complete misunderstanding. So I understood that this is now going into approaches that formerly were index-based, but could you dare elaborate a little bit on that? So is this then like a hybrid model where you have then both representations in parallel, like an index-based and the vector embedding, or?
Okay. I think I get your question. So when I say we are building an index with vectors, it basically means that we are not using an inverted index like traditional keyword search engines, where we store the words and then the IDs, where the document IDs where these words occur in. When we say we build a vector index, or an index consisting of vectors, we basically store the vectors in an index, which just means that there are algorithms which are capable of searching in these data structures efficiently by, for example, dividing the whole vector space in smaller segments. And by that way, you can say, okay, let's say I have 1 million vectors indexed and I divide it into 10 segments. The first approach is, that's now very naively depicted from me, the first step is find me the best segments to find similar vectors. And then within this one segment, let's say, a narrower search is done afterwards. So we're not really combining inverted index and vector search indexes in that case. This is a whole new kind of data structure, completely unrelated basically to a inverted index.
Yes, thanks a lot. Now I got it. Yeah.
Perfect. So the one thing I wanted to show is, of course, not where I expected it. So if you have another question in the meantime, feel free to shoot that at me while I try to find what I wanted to show. Oh yeah, I think I know where I can find it. So what I can, in the meantime, at least, let's say, recommend if you are into the search topic is a book called AI-Powered Search. I'll share my screen in a minute. Just a second. Chapter 10. No. Chapter 13. That should be it. So I'm now showing code that I have not written. Which is always tricky to explain to others, but nevertheless, we'll get there. So the book I can recommend is called AI-Powered Search, and I'm just using their code repository now, AI-Powered Search, just to give you book as well. It's not published yet, but it is purchased, or you can purchase it as a so-called Manning Early Access book, which means you get access to all the chapters that are already written. And one of the already written chapters is Semantic Search with dense vectors. And that's what I'm now showing, because that's the easiest thing, at least, that I can show without really conflicting anything that I have on my notebook. So what is in fact used here is also a BERT-based model. In that case, it's a sentence transformer. And I'll skip the verbose output here when this is loaded. Next case is there are a couple of phrases, and these phrases are then encoded into embeddings with this sentence transformer. So what we have after this step is we have per phrase basically the embedding feature vector, which we encode in that case 768 dimensions. So what we see here is for a phrase, but you can imagine that being a document, 768 dimensions full of information. And that is what we basically then can store in an index afterwards. And when we search for, basically anything, we also convert that into a 768 dimensional vector, and then we can compare it to what we already have indexed. And what this example hopefully depicts is no matter how many words we have, whether that's only one term or in that case a phrase or a whole document, we always have these 768 dimensions in that example at least, which we store and which we then use for retrieval.
So this BERT model is basically already built to convert an arbitrary sequence of words, no matter how many words, to a 768 length vector.
Exactly, yeah.
So it's already embedded. So I need to look up. I mean, I knew about the BERT model for single words. And I mean, and then my curiosity was, okay, let's say you have a sentence made out of 12 words. I thought you would have 12 vectors, and then you somehow need to transform them into a single vector, and averaging obviously would not be a good idea.
Okay.
At least. So, but then this is a special case BERT model that further reduces embeds the embedded vectors possibly or something.
Yeah, so in that case, I would say this Roberta thing that works really well on, let's call it sentence level. So if you have pieces that extend the sentence level, you would probably go for another model. But there are, well, let's say, some models out there where you don't really need like use the whole Wikipedia to train your own stuff, but where you can at least get to 70, 80, 85% maybe, and then do the fine tuning on this, well, large model then.
Okay. Thank you.
Okay, not in time answered, but answered eventually.
Yeah, checking the time, it's already 5 o'clock. Daniel, thanks again for this cool and very insightful presentation. I also copied the link to the GitHub repo that you just showed. And yeah, if you could also share the link to this, what was it called? Manning Early Access?
Yes, yes.
Didn't know that before. Very interesting. So what a model to publish not even finished books.
Yeah.
Is Game of Thrones on there?
Very good, very good. So let's conclude this eMeetup. If there are more questions, please just stay in the Zoom meeting. To all the others, have a good week. Let's see each other next week. We have also very interesting topic then with Jona Kresse. He gonna say something about personalization of news articles on news portals, and that you see like the most relevant stuff there, depending on where you live. So yeah, let's meet again next Tuesday, and yeah, stay safe. Have a good time. Bye-bye.
Bye, thank you.
Daniel.
Thanks a lot, bye.